In this chapter, we are discussing thermodynamics. Now, the definition of thermodynamics is one that you're not actually going to encounter until a little bit later in the chapter, but I think it will benefit us if we go ahead and discuss what that is, because it's going to give you an overall general idea of the topics that we're going to be talking about in this chapter. So the definition of thermodynamics, and again, you'll see this later, is it's the study of relationships and conversions between different forms of energy. Now, if you've taken a physical science class at some point in your past, you may remember talking about potential energy and kinetic energy. There are other types of energy as well. You've got nuclear energy and you've got heat energy, all different types of energy. But one thing that you may remember is that energy can't be created or destroyed, but energy can be converted from one form to another. And so what we're talking about here is the conversion of energy from one form to another as a result of a chemical reaction. Now, one of the properties that we discuss in relationship to thermodynamics is enthalpy. Enthalpy is just very simply a measure of how much potential energy a system has. And we use a capital letter H to designate enthalpy when we're talking about enthalpy. Now, it's very, very difficult to measure exactly how much potential energy a system has. It is a little bit easier to measure the change in the amount of potential energy that a system has. And so in chemistry, that's actually what we tend to measure, is this change in potential energy of a system. And anytime you see a delta, that stands for change for or change in. It's a Greek letter delta, the capital delta. And so delta H stands for the change in enthalpy, or how much change in potential energy, rather, a system is going to undergo. Now, the potential energy can change in one of two directions. It can either increase or it can decrease. So if my potential energy gets converted to kinetic energy. So if you think about a combustion reaction where you take a piece of wood and you burn it and it gives off a lot of heat, that wood contained a lot of potential energy, and when it burns, then what happens is that the molecules in the surroundings start moving a whole lot faster. That's why if you have a campfire, everybody wants to huddle up close to it because of the heat that it gives off, especially if it's a cold fall night when you're doing that. So the potential energy changes to kinetic energy, and that results in an increase in temperature. If a reaction gives off heat and the surroundings rise in temperature, you have what's called an exothermic reaction. The prefix exo means out of. And so you've got thermal energy or heat coming out of the reaction and warming up the surroundings, okay? So what's happened is that if you think about this pile of wood that you're burning, there was a lot of potential energy in that wood. And so you've given off a lot of the energy. It's turned into kinetic energy instead. And so the amount of potential energy that my products have, so after you burn the wood, you've got water vapor, you've got carbon dioxide, you've got some ash left over. So the potential energy of the products is less than the potential energy of what you started with. And so when I subtract those two in that order, I'm going to end up with a negative number. So anytime I have an exothermic reaction where I have decreased the amount of potential energy that I have in the system, my delta H is going to be negative. Now, the opposite situation is one where you're going to absorb kinetic energy from the surroundings, and so potential energy is actually going to increase while your temperature is going to go down. An example of this is if you've ever had an athletic injury and you have one of those activated cold packs where you take the cold pack and you kind of scrunch it together to activate it, and then it turns cold. Well, what happens is that kinetic energy is being absorbed from the surroundings, and so you're actually going to increase the amount of potential energy in the system, so your temperature is actually going to drop. In that particular case, the potential energy of your products is higher than what you had for the reactants, and so the difference is going to be a positive number, so your delta H is going to be positive. So of all of this, what's most helpful to remember is that an exothermic reaction has a negative delta H, and an endothermic reaction, one that gets colder, is going to have a delta H that is positive. Now, in a chemical system, your potential energy is contained inside of chemical bonds. And so one way to calculate the enthalpy or the change in enthalpy of a system is to calculate how much energy is in chemical bonds. It takes energy to break bonds, and it takes energy to make bonds. So we're going to run through an example here of what it would look like to calculate the energy of a system based on the types of bonds that you have. So we will make some space up here on the board so I can show you what that looks like. The reaction that we're going to look at for this is the production of ammonia. And so I'm going to start with N2, which is a gas. And I'm going to combine that with hydrogen gas, and that will make NH3 or ammonia gas. Okay, now you'll notice that this isn't balanced. In order to balance this, 2 nitrogens would have to be put on this side. That gives me a total of 6 hydrogens, so I will need a 3 here. Okay, in order to look at the type of bonds that you have, if you remember when we talked about bonds before, there are single bonds, there are double bonds, there are triple bonds. A triple bond is much, much stronger than a double bond. A double bond is stronger than a single bond. So in order to break those bonds requires a specific amount of energy. And on the table in your textbook, you will see that you have a table for specific kinds of bonds and how much energy it takes to make and how much energy it takes to break those bonds. So the first thing we have to do in a situation like this is say, okay, what do these molecules look like? So if I have 2 nitrogens bonded together, you should recall that nitrogens have 5 valence electrons, and so I'm going to draw them like that. And so in order for these atoms to each have an octet of electrons around them, these electrons will pair, these electrons will pair, and these electrons will pair. So what that will end up giving me is a triple bond in that nitrogen, okay? Hydrogen, you'll recall, only has 1 valence electron. And so hydrogen doesn't obey the octet rule. It only needs 2 electrons in its valence orbital or in its outer orbital to be stable. So hydrogen just has a single bond in that molecule, but don't forget that we actually have 3 of those to make this balanced equation. Then when I get over here to the NH3, again, your nitrogen has 5 valence electrons. Each one of the hydrogens just has 1 valence electron. So the hydrogen needs 1 more, the nitrogen needs a total of 3, and so what we're going to do is we're going to have a single bond to each one of these hydrogens. That gives each hydrogen 2, and it will give the nitrogen then a total of 8 to obey the octet rule. So start with the Lewis structures so that I know what my structures look like. Now, in order to calculate this, what you need to do is say, all right, if I'm going to completely break this down into the constituent elements, the constituent atoms, the first thing I have to do is I have to break this triple bond. And the table in your book tells you that it takes 945 kilojoules per mole to break a triple bond between 2 nitrogen atoms. And in this particular reaction, I have 1 mole of those that I need to break because there's a 1 in front of here, okay? To break hydrogen bonds, again, if you look at the table in your book, you will see that it takes 436 kilojoules per mole to break a hydrogen-hydrogen single bond, but I have 3 moles of those that I'm going to have to break because there's a 3 in front of the hydrogen. Okay. Now, I have all this energy that it takes to break these bonds. I have to use energy to make these bonds. So how much energy is it going to take me to create these bonds over here? Well, here I have 3 nitrogen-hydrogen bonds, and in order to make those, it's 390 kilojoules per mole to make one of those bonds. There are 3 of them present in this molecule, but I have 2 moles of molecules present, so that's going to give me a total of 6 moles of bonds that I have to break, because I have 3 times 2, which makes 6. Okay, so this is the energy that's going to be required to make these bonds. So then what I end up with is I have 945 kilojoules here, because your moles are going to cancel out. If you take 3 times 436, that's going to give you 1308 kilojoules, because the moles will cancel out. And then if I take 6 times this 390, that's going to give me 2340 kilojoules. So now what I want to do is I want to compare what was on my product side with what is on my reactant side. On my product side, I have a total of 2253 kilojoules. On my reactant side, on my product side, I have 2340. So you can see that this number is bigger than this number. And so if I subtract 2253 kilojoules minus 2340 kilojoules, that's obviously going to give me a negative number. That's going to be a total of negative 87 kilojoules. And so that's going to be my delta H for this reaction. Now, do you remember what I had on the board before? If this is a negative number, what kind of reaction is it? Well, if this is negative, that means it is an exothermic reaction, which means that heat is going to be given off there. There is more potential energy in my products than there is in my reactants. And so, therefore, the energy to break the bonds that is released when I make the bonds, I'm actually going to have that energy left over. So therefore, it does become an exothermic reaction. So you are going to be practicing in your assignment today calculating changes in enthalpy for reactions. You will have to have Lewis dot structures drawn first. The next time we're together, we will talk about how that's not the most efficient way to do it, that there are better ways to do it, and we'll talk about why, but we're going to start with this first because this is really the basis of where enthalpy comes from, is it's the amount of potential energy that is stored within these bonds.